our session.
Yeah, thank you, Cynthia. So our first speaker for today is Walt Meier, and he'll be telling us about some sea ice remote sensing products that are available at NSIDC for seasonal forecasting, and also give us a look back at the Arctic sea ice conditions in 2021.
All right, thanks, Angela. Let me share my screen here. Okay. All right, thanks. At NSIDC, we're in University of Colorado. We're in traditional lands of the Cheyenne, Arapaho, and Ute tribes. And so I will, first I'm going to start with the look back at roughly the last year, just kind of a quick overview of some of the outcomes of the sea ice in the Arctic. Probably seen this before, something like this. So this is just updated now through the March of 2022. Last year, September was a bit more moderate than what we've seen in recent years. It is the highest minimum since 2014, but we're still in a very significant, strong downward trend, as you can see, with a lot of year-to-year variability. A lot less variability in March, but still a significant downward trend, 2.5% per decade. And roughly in terms of absolute kilometers square, about half of the trend. And this last March was again a little bit up, a little bit above the trend line, but not much of a change, pretty much in line with the last few years. And we look at just the spatial distribution at March of 2021 through September 2021 in the middle, and then March of 2022. You can kind of see the maximum through to the minimum and then the maximum. I think comparing the two Marches, one of the things that if you look, you'll see the Bering Sea has a little bit more coverage this last March than in 2021. The Sea of Okhotsk had quite a bit less coverage. That's kind of the main differences. There's also, both in 2021 and 2022, but more pronounced in 2022 here, kind of a pretty strong cut in of open water in the Barents Sea north of Novaya Zemlya, which I think is kind of interesting, probably related to some maybe some Atlantic water, warm surface waters coming in and penetrating deeply. Focusing more recently, again in March, one of the things that was, I think one of the more notable things the whole winter, and particularly March, we had a really strong cyclonic system come in along the coast of Greenland and really pump in some strong northerly or northward winds, winds from the south, as you can see there. And then that brought in a lot of heat and moisture. This is a water vapor transport animation by Jessica Voveris at the University of Colorado, a graduate student here, working with Mark Serez. So you can see a pretty strong pulse there. And it brought, like I said, a lot of moisture and a lot of warm air. On the right is the NSEP temperature anomaly for the 14th of March. And you can see kind of a bullseye there of almost 15 degrees C near the North Pole. So really a lot of very warm air up there. Was, if you look at if I showed the absolute temperature, very close to the melting point. It may have had some surface melt at or near the North Pole. If not, it was quite close. Looking over on the left, it did kind of a number on the East Greenland sea ice. This is from the University of Bremen, AMSR 2 data. Gunnar Spreen originally presented this at the Arctic Science Summit Week Science Day, so I'm kind of stealing his that he's found here. And you can see you went from March 13th to a pretty solid consolidated ice cover along the east coast of Greenland to a pretty broken up, a lot of rubbled ice. Probably you can see some openings in the ice cover along the coast of Greenland. One of the things with this is in March, so it's towards the end of winter. We are actually past the maximum at this point. There was an early maximum February 25th, but still pretty cold all in all up there. So, this heat pulse went up. I don't know if it really is going to affect things too much. I mean, the East Greenland, the ice is excellent anyway. If there was any melt, it probably froze up pretty quickly. May have altered the snow a bit, but I don't know if I don't think really this have a big effect in the summer melt season. But it does seem to be a pattern that we're starting to see more often. We've seen some of these pulses years that are penetrating up into the Arctic and farther up into the Arctic than what we would normally have seen. At least it seems so. So looking at the thickness, we can look at the thickness from some of the new altimetry data, ICESat-2 and CryoSat-2. CryoSat-2 combined with the SMOS sensor, which is a passive microwave 1.4 gigahertz, which is good at detecting thin ice. And so it kind of complements the altimetry that is better in the thicker ice regimes. This is from the Arctic report card. So this is about a year ago. We don't have the latest data here yet, but it showed that 2020, 2021 was thinner than the previous couple years. And the CryoSat-2 data, I'm not showing that here, goes back to 2010, and it was the thinnest in least voluminous ice in the last 10 to 12 years, basically, in the record. And that this kind of leads into the next part, which is actually looking at some of the newer products, including the altimetry products. I'm going to focus here on US products particularly. So I'm not going to talk further about the CryoSat-2 SMOS or CryoSat-2 products. But those are obviously quite valuable, particularly for seasonal forecasting. In terms of forecasting, one of the big efforts that is going on that I've been involved with since it started was the Sea Ice Outlook in 2008, focusing on the seasonal prediction of September extent. This is now managed under the Sea Ice Prediction Network 2. This is the second funding part of this. It led by Bhatt at University of Alaska Fairbanks is the PI, University of Washington, University of Colorado, and I should have put on here ARCSIX as well, is a big partner in this in organizing this. Funding comes from multi-agency. It really, I think, fits with the ARCSIX, the interagency aspect, as well as international. And we are in our last year of funding. So this outlook is coming up here in the next couple 3 weeks or so. You'll probably be hearing about it, and the start of it starts with the June initialization, June 1st. But we do have a proposal submitted, again led by Bhatt, that is hopefully going to carry this on and enhance and extend this, and particularly focusing on increasing skill and better understanding and improving and reducing the forecast errors. And also fostering more interaction and collaboration within the community and via community portal. So hopefully you'll be hearing more about that soon. In terms of the data, we have currently two data sites. There's a sea ice data site at NSIDC for SIPN that focus on the observational data, concentration, extent, thickness, etc. These are data, some of these are at NSIDC, but some of these are what we call brokered. They're at other institutes that we link to provide visibility. Not all of these are in near real time. In fact, probably most of them are not, but they are potentially valuable for developing forecasts and evaluating forecast models. And then there's the University of Washington data portal of model forecast, which is funded through ONR. And this kind of collates together the different model forecasts that are submitted, and does shows some evaluation of those and provides information and sources of information. Oops. So some of the specific data to kind of highlight here. This has been around for a while, this CryoSat-2 sea ice thickness, but it was not updated for a while, but has recently been restarted processing. And so this is NASA Goddard product for using the CryoSat-2 data and compositing a 30-day sea ice thickness product. It does have a 40-day lag, and so it's not necessarily timely for forecasting. but I think still potentially valuable. There is a quick look kind of time product that will hopefully be updated at some point in the not too distant future. I've talked with Nathan about this, and probably later this year, not in time for this year's seasonal CI season, but hopefully be available maybe for next year. But the regular product that is ongoing here now. We also have a new ISAT2 sea ice thickness product from Alec Petty and others, also at NASA Goddard. ISAT2, if you're not familiar with the data products, the standard data products have been around for since I think May of 2019. The launch was in 2018. But the standard product for ISAT2 for sea ice is elevation and sea ice height and sea ice freeboard. So there was not a sea ice thickness product as part of the standard products from ISAT2, but Alec Petty and colleagues have put together a product that has both long track, so for each individual track, a thickness, and then a gridded product, and that uses the snow depth from this NESOSIM snow model, which I'll talk about in a minute, to invert or convert the freeboard to thickness. And again, these are not real time, but I think again valuable for evaluation of models, at least in hindcast mode. There is a quick look product now out for ISAT2. This is just in the last few weeks, I guess. And it's again freeboard, not thickness, but again potentially useful. And this goes from the standard products being about a 45-day latency to only about a 3-day latency. So it doesn't qualify per se as near real time, but I think still quite valuable and low latency. So it lacks some of the quality control, some of the higher level corrections that to get the orbit in the actual elevation freeboard nailed down really precisely. So it's not quite as accurate, but I think it's quite good. The science team that agreed to do this looked at these data and found that they are accurate enough to be useful. And so this is just an example of some of the data. These are track data. So for each track as it comes in, can give you the freeboard along the track. And there's some other ones, but this is the other quick look ISAT2 products, but this is the one relevant for sea ice, or most relevant for sea ice. So this is quite exciting. This came from, I think, from a community desire to have ISAT2 data available more quickly to the community, particularly for forecasting. So this was a response that this again was not in the original plans for ISAT2, but they recognize that the desire of the community to have a more real-time, closer to real-time product, and they put that together. And this is distributed through the NSIDC, NASA DAC, along with the other products. Another product, or a couple other products that are available, again, not in real time yet, is snow cover. I mentioned the NESOSIM, which is the NASA Eulerian snow on sea ice model. And that's included in the ISAT2 thickness product as a field. The Lagrangian snow distribution product, which is developed by Glenn Liston and others, Glenn Liston at Colorado State, is archived as an NSIDC product. Both of these use reanalysis basically to distribute snow cover or snow on the ground, snow precipitation on the ice. The Liston product does a Lagrangian advection to move the ice around and the snow cover on top of it, and a snow model also to do drift. The NESOSIM uses ear reanalysis. And so these are really important for understanding, certainly understanding like the freeboard and converting to thickness, but also just the state of the ice cover overall, I think, in the Arctic. And we have not had very good snow depth and snow cover information previously. And so this is, I think, really exciting to have these data products available on the snow cover. The other final thing I'll just mention, a lot of interest in terms of forecasting, particularly for regional forecasting. And there's been a regional mask around developed originally at NASA Goddard, applied over the years. And we put together a new one that it's not quite out yet, but we have at least the polar stereographic version of it. This is showing that, and basically we tried to do a more rigorous and also something that has more provenance to it, something less ad hoc. We use International Hydrographic Organization definitions as a starting point. Added some regions as well. So if anyone's interested in this, let me know. But this will be published fairly soon from NSIDC, hopefully in different grids, East 2 and polar stereo, and different resolutions for different applications. So we think this will be of interest to the community. So I just wanted to mention that while I had folks' attention. And then finally, these are just listing kind of our main passive microwave or not only passive microwave, main sea ice concentration and extent data that are used. We have the NOAA NSIDC Climate Data Record, the NASA team product from NASA Goddard, and real-time processing at the NSIDC DAC. That's used for the sea ice index that we traditionally use for our analyses of sea ice, and it's been used by the sea ice outlet. And then we also have this MAISY, which is the multi-sensor analyzed sea ice index produced at the National Snow and Ice Data Center, bring in different data sources and expert analysis. And it has a higher resolution, 1 kilometer or 4 kilometer than the passive microwave. So that's also potentially useful. So with that, I'll finish up. Don't have any kid pictures or cute pet pictures, but we have a den of box fan den behind our backyard. So this is one of the kits we took recently as the cute picture to end. So I'll end there. Thanks.
Thank you, Walt. That was a great talk. I think we have time for a couple of questions for Walt. So please, you can raise your hand or just shout it out or place that in the chat box, and we're happy to get those questions answered.
And I see Betsy at ARCSIX, Betsy Turner put out that, like I mentioned, we will be soliciting contributions here coming up towards the end of the month. So look for that if you're interested in submitting.
I have a question, Walt. With the number of thickness and freeboard products available at NSIDC, is there an easy way for users to sort of cross-compare what the errors on all those products are, other than looking at the individual data set metadata?
I would say not easily. It's, they're quite different products. The ISAT, they do have some quality information and I think some error statistics, so you can get a sense of what the errors are, definitely, at least relatively speaking. But comparing them, I think, is challenging because particularly like if you're trying to look at like Cryosat-2 versus ISAT-2, it's a radar altimeter versus a laser altimeter. They have different footprint sizes, different sampling. They penetrate to different depths. The radar tends to penetrate through the snow. The laser tends to reflect off the surface of the top of the snow cover. So I think it's a real challenge to do that. So I think that's an active area of interest, and I think there's definitely value in trying to look at that and trying to get a better understanding of that. I'll mention there's been one or two papers, at least, in terms of looking at directly ISAT-2 and Cryosat-2. Ron Kwok and Sarah Kasimi have published on these to actually look at getting potentially snow depth from those, and have, I think, shown some success. And so that indicates there's some compatibility between these, but in terms of directly trying to really directly compare errors and maybe further combine these, it's a challenge. And so I think that's a remaining challenge that's still out there. as these products are still relatively new, and particularly ISAT-2 are quite new. So I think there's a lot of work going on, and I hopefully we'll see more on that in terms of defining the errors and being able to compare the errors. But I think that's a great question and great thing to look out for in the future.
Yeah, thanks, Walt. Any other quick questions? All right, so next we will hear from Amy Solomon, and she'll be telling us about developing higher order forecast products to support aircraft campaigns to observe coupled sea ice atmosphere interactions. And I think she'll also tell us about some work she's doing to support the upcoming ARCSIX project.
Can you see that in presentation mode?
Yeah, looks great.
Okay, great. Yeah, thank you for the opportunity to talk about the work we're doing to support the ARCSIX campaign. My name is Amy Solomon. I'm at the University of Colorado series and the NOAA PSL Physical Sciences Laboratory. And this talk is about forecasting for the ARCSIX campaign. And it's a campaign supported by the NASA Science Mission Directorate, Radiation Sciences and Cryospheric Programs. And they solicited a call for proposals in the ROSES 2021 call, and they reviewed all the proposals, and they will be forming science teams, hopefully by the end of this month. And the campaign science plan was developed by Sebastian Schmidt at CU and Patrick Taylor at NASA. And the NASA program managers are Hal Mehring and Thorsten Marcus. So the overarching goal of ARCSIX is to quantify the contributions of surface properties, clouds, aerosol particles, and is there some way I can reduce the size of this? I can't really read the full. Okay. So the contribution to the Arctic summer surface, radiation budget, and sea ice melt during the early melt season. And in the writing of the science plan, there were 3 questions that were defined that will be the focus of the campaign. The first is about radiation, and it's what is the impact of the predominant summer Arctic cloud types on the surface radiative surface energy budget. The second science question is focused on cloud life cycles. And the question is, what processes control the evolution and maintenance of the predominant cloud regimes in the summertime Arctic? And the third question is focused on sea ice. And the question is, how do the two-way interactions between surface properties and atmospheric forcing affect sea ice evolution? And then a third question was defined on remote sensing and modeling. And that is to enhance the long-term space-based monitoring and predictive capabilities of Arctic sea ice, clouds, aerosols by validating and improving remote sensing algorithms and model parameterizations in the Arctic. So 2 aircrafts will be flying for this campaign. One will acquire in situ aerosol, particle, cloud, and surface properties along with radiation below, above, and inside a cloud layer. While the second plane will be flying higher and will be a bridge to satellite observations by surveying with heritage and novel remote sensing instruments from above. And so this will require near simultaneous characterization of radiative fluxes, surface and cloud properties that will address the science questions 1 and 3. And there will also be statistical sampling of cloud vertical structure, temperature and humidity profiles complemented by simultaneous remote sensing. And this will address science questions 2 and the remote sensing and modeling objective. And so to extrapolate the spatially and temporally limited fields in the observational campaign, the airborne data will be integrated with the remote sensing, observations, and model simulations. And targeted sampling of distinct regimes defined by cloud type and the associated prevailing surface and meteorological conditions will enable more useful combinations of airborne, satellite observations along with model simulations. So the deliverables for the campaign will be a statistically representative characterization of radiatively important lower tropospheric cloud systems. And this is cloud systems that are difficult to observe from space. So that's one of the critically important aspects of this campaign. And this will be in a manner that enables the identification of key cloud evolution processes, as well as the quantitative representation of such processes and models on all ranges of scales. And also the characterization of surface reflectance and its spatial and temporal variability in response to precipitation and melting, to capturing sea ice surface properties and thickness evolution, including snow depth in spring, to melt pond coverage and size distribution, and coevolution with atmospheric conditions through recurring measurements of the same sea ice flows from pre-melt onset through the early melt season. And also the evolution and innovation of remote sensing techniques for Arctic aerosol cloud and surface properties that enable the long-term observations. So we did some dry run exercises last year, and what we found is that there were two regions that we really wanted to focus on. And so in this map here in the upper right, the flights will be out of Thule and or Svalbard, depending on the aircraft that will be used for the campaign. That's still being determined and worked out. And this map, just to orient you, the upper left, this is Licktock Point, so the Alaskan coastline. And in the lower right, this is Summit, so the top of the Greenland ice sheet. Oops. And so these circles are showing the loiter time. So with the green circle, you can see with the in situ aircraft, you can have a loiter time of about 4.5 hours. And so in the writing team, in the science plan writing team, different regimes were defined, as well as their likelihood of being observed and the priority they will play in the flight planning. And so that's what's shown in the lower right. So the regime with the highest priority is the one that was had less likelihood of being observed. It is also critically important for the campaign because it's the clear sky regime, and it allows observations of the surface characteristics and the evaluation of some of the satellite products of these observations. And so the second most important regime that was defined is the advective events and the aerosol transport events, because one of the main research focus of the campaign is going to be cloud aerosol interactions. And these events have a very low likelihood, but if they are able to be observed, they will be critically important for our understanding of cloud aerosol interactions. The regimes with the next lower priority are the advectively coarse clouds and the quiescent low cloud regime, as well as flights of opportunity. And so we'll be flying from the north of Greenland, where in recent years, there have been some very interesting polynyas that have formed there, as well as transects from the north of Greenland to the North Pole in order to observe the change in the spatial and surface characteristics as you go along that transect from north of Greenland to the North Pole. The other is the air mass modification, as air masses are advected either from the open ocean through the Fram Strait to over the sea ice, or the other way around, air masses that are transported from the sea ice out over the open ocean. So we did these dry run exercises with a model that I adapted from the Regional Arctic System Model, or RASM. And our model is called CAFS, or the Coupled Arctic Forecast System. And the components of this forecast system are the WRF atmospheric model, the Los Alamos sea ice model, the Los Alamos POP ocean model, and the NCAR land surface model. And all components are run at a relatively high resolution of 9 to 10 kilometers. And so this is showing in the upper left, this is the RASM model. So it is focused on climate simulations. So you can see this domain is quite large, and it includes all of the Arctic drainages and mid-latitude storm tracks. And the atmospheric model is run at relatively high a coarse resolution, medium range resolution, 50 kilometers, and there's no initialization of sea ice. And I know that they are starting to work with this model, using it for more like decadal forecasts. So they are starting to use this model for more forecast applications. And the lower right is the CAPS model that we used for the dry run exercises for the ARCSIX campaign. And you can see the domain is much smaller. So it's just the Arctic basin and the land around it. And it has high resolution components, so much higher resolution than the RASM model. And it's initialized with the GFS analyses, AMSR2 sea ice concentration, and the NOAA blended SSTs. So this is a very simple way of initializing a model. We hope to be able to use more sophisticated initialization techniques that are now being developed at NOAA. And we force the model with the GFS 3-hourly forecasts and analyses at the lateral boundaries. So we have been using the CAPS model for ship-based campaigns and for model evaluation. We started using this model in 2015 to support the Sea State campaign that took place from October 1st to November 5th. And the reason why it was so important is that the ship that was used for this campaign is called the Zakuliak, and it's a light icebreaker. And as you can see in these small figures, these 9 small figures, during this freeze-up season, the ice was changing really rapidly. And the focus of this campaign was to observe ice-ocean interactions at the ice edge. And so this light icebreaker would go into these bays, and there was a real danger of the bays freezing up. And so they needed to know, have some idea, a 5 to 10-day forecast of how the ice would evolve, because if they got frozen in, they would not be able to get out. And so this was our first campaign that we supported. And then after the campaign, we used the observations to evaluate the model, and that's what's shown on the right. And so we started to, this is a fully coupled system. So ocean, ice, atmosphere. And so we were able to use these observations, the CTDs in the ocean, so that's the blue. And then the observations taken from the ship, that's the light blue and the yellow. And then the soundings, which is the red. And this is showing the model minus observation, so plus or minus 2 degrees for a 5-day lead time. And what you can see is that in the ocean, we have very, pretty small, we didn't expect them to be so small, but that we have a reasonable initialization of the ocean. But in the near the surface and in the lower part of the atmosphere and up to the top of the boundary layer, you can see that the errors are much larger. And so we're getting about 2-degree errors near the surface that decrease and become negative at the top of the boundary layer. And what this is saying is that the model is having a difficult time maintaining a stably stratified boundary layer. So we also use the CAPS model for ice floe-based campaigns. On the left is some of the forecast products we developed to support the Mosaic campaign, which ended in the fall of 2020. So it was the year-long drift experiment that ended about a year and a half ago. And so the German Weather Service was providing forecasts to support the operations for the ship, but there weren't any specialized forecast products to support the scientists. And so we wanted to be able to fill that gap with some of these CAPS forecasts. So what we provided was the evolution of the near surface conditions and the changes in the sea ice. For example, for the UAV applications, for some of the boundary layer observations, and also so they can get forecasts on the evolution of the sea ice in the regions of the ice camps that were 10 to 20 kilometers away from the Central Observatory. In the middle, this is showing we were supporting the ARCSIX campaign. So we've been doing that the last 3 ARCSIX campaigns. So the Navy has a campaign every other year in the Beaufort Sea where they test some of their new instruments and some of their new observational techniques. And so this is from their last campaign, which ended about a month ago. And so we provided these forecasts to help them decide which ice floe to put their ice camp on. And then after then, we provided these forecasts so that they can get an idea about how the surface conditions will be changing over a 10-day period. And so this is a snapshot from our webpage. So not only do we provide forecasts in whatever format is useful to the campaign, whether it's text or NetCDF, but we also have these real-time animations that are available on our webpage. And on the right, this is from the SIDVEX campaign. So that stands for the Sea Ice Drift Forecast Experiment, which was initially developed to support the Mosaic campaign because it was important to know how the campaign was drifting in order to be able to order satellite products. But it became sort of a project on its own. And so not only do, I think there's over 10 modeling centers are providing these daily forecasts. It was originally around the Mosaic campaign and the Polar Stern, which was the central observatory for the campaign. But people are providing forecasts for buoys all over the Arctic from the International Arctic Buoy Program. And so now we have this database of forecasts of sea ice drifts that we're going to be using to evaluate the sea ice dynamics in the models. So when we were doing these dry run exercises for the ARCSIX campaign, we wanted to develop these higher order products because we don't want to just be able to forecast near surface air temperature, surface winds, but other things such as cloud formation and other dynamical processes such as potential vorticity anomalies and what impact they have on the surface. So this is one of the animations that we developed for the campaign. This is a cross section from Svalbard to the North Pole, and it's showing forecasts. So the animations are forecasts from 0 to 5 days of the potential temperature. This is from 0 to 10 kilometers, the wind speed and direction, and the regions in the atmosphere where liquid cloud formation is forecasted to occur. And this is showing some of the other products. So on the left, this is north of the Fram Strait, so over the sea ice, 0 to 10 day forecast from 0 to 1 kilometer of potential temperature, wind speed and direction, and where liquid cloud formation is going to occur. And I just took this from our webpage. It's not any specific event, but what this shows is that we will be forecasting how the variability will change in time and height north of the Fram Strait and south of the Fram Strait in order to get a better understanding of how air masses are evolving as they're being ejected across the Fram Strait. And on the middle and the right, these are mediograms, one north of the Fram Strait over the sea ice, one south of the Fram Strait over the open ocean, showing wind speed and direction, ice thickness and snow depth, surface pressure, 2-meter temperatures, snowfall and rain rate, and shortwave down, long wave down, and albedo. And these products are, we create them every day, and they're available on our webpage to anyone who wants to see how these forecasts evolve. So these are some of the other products that we developed for the dry run exercise last year. The left is showing the potential vorticity on the 310 Kelvin surface and with the colors, and then the black lines are showing the surface temperature. And so this is really critically important. I'll just move up a little. So if you see, so you can see this in the center of this domain, these orange and red colors are showing large positive potential vorticity anomalies at the tropopause. And the black lines are showing the impact that this potential vorticity anomaly and the winds associated with this anomaly are having at the surface. And so you can see that you can get very large anomalies at the surface associated with these atmospheric phenomena. And this is critically important for forecasting of cyclonic events. And so these are some of the newer forecast products that we're using in the flight planning for the ARCSIX campaign. And on the right, this is showing trajectories, and the colors are showing the surface pressure. And so this is also to be able to see how air masses are evolving and how they're moving in time in order to be able to forecast the evolution of the air masses so that we can develop these flight plans to track these air masses. So this is one of the dry run exercises that we did. This is to observe an advective event. So in the middle figure, this is from the University of Leipzig flight planning tool. And you see these colors and these arrows along the east side of Greenland. So this was integrated vapor transport, a very significant event of transport through the Fram Strait. And on the left is one of the products that we provided with the CAPS model. This is a cross-section from Thule to Svalbard. So approximately where this blue line is here in the center figure, to look at, so this is an animation, this is just a snapshot, but to look at how the clouds are evolving across the transect and how the temperatures are changing for our flight planning. And on the right, this is one of the examples of the flight planning activities that we put together. So the blue lines are showing the high flyer, so which can travel much longer distances, and it will scoping out whether the forecast is accurate, doing these transects across the air mass, and then along the core of the air mass. And then the red lines are showing the in situ plane, which would have much shorter legs and measure in depth the air mass, both up and downstream, to see how it's evolving in time. This is an exercise that we did to observe quiescent low clouds. So the left is showing the liquid water path from the CAPS model. And in the black line, you can see this is Greenland. So north of Greenland, there were very large liquid water path, but very low winds, which is indicative of these low cloud regimes. And on the right is one of the flight plans that was put together to observe these low clouds, where both the low and high flyer would be flying together in order to get the measurements above and below the cloud system. So we want to be able to integrate lessons learned from some of the recent campaigns, such as the HALO AC3 campaign that just finished. And some of the people that are very involved in this campaign were also involved with the flight planning for this campaign as well. And as you can see on the right, these really interesting flight plans. So they had 3 planes, we'll just have 2. But the blue is the high flyer, and then the orange and the black are the low flyers. And you can see these very interesting flight plans that they put together in order to observe some of these advective events, some of these air mass modification events. And we'd like to incorporate that into the dry run exercises we'll be doing in this year. So going forward, the science teams will be formed very soon. We'd like to integrate these science teams into our dry run exercises that we'll be beginning very soon. And we want to continue to advance some of our forecast product development to be able to forecast these specific atmospheric phenomena, such as the potential vorticity anomalies that play such an important role in the evolution of the surface conditions. So we want to be able to forecast these atmospheric and coupled phenomena in a way that they can be integrated into the flight planning in a meaningful way. So thank you very much for your attention, and I would love to hear your questions.
Yeah, thank you, Amy, for a wonderful talk. Do we have questions for Amy?
I have a question. Hey, Amy, great presentation. I learned a lot. Will some of, can you tell me a little bit more about your transport, aerosol transport studies? Were you going to look at things like fire or pollution? Or was it, you said something about transport from the ice. So anyway. Well,
the transport would be from the open ocean over the ice. And it isn't really focused on fires or pollution. It's, there will be an aerosol transport model running that we'll also be using for our flight planning activities. But there really hasn't, I mean, I see that Sebastian has his hand up, but there really hasn't been much discussion of fires or pollution. I don't know if that should be taken into account in some of our planning. Sebastian, would you like to address that?
Yes, just so much that as far as the transport goes, there will also be dedicated forecasters for aerosol transport. Hopefully, it depends on the selections, of course. So this is pre-decisional.
Sebastian, you have a question?
Oh, I just had a comment. I mean, I just wanted to say that this, I appreciate the presentation was great. I was actually part of AC3, so I was up there in Sweden, as you know. And I just wanted to say that since I will be going to Leipzig soon, I'm really looking forward to our dry run exercise. With of course, again, the caveat that this is pre-decisional, so we'll be starting our dry run before the selection has been officially made. So that's all I wanted to say. But this is great because we're going to be bundling your resources with those of the University of Leipzig. It's a great combination, I think.
Melinda has a question as well.
Yes, I'll ask Amy a quick question, but there's a question in the chat too for Walt. But Amy, I was wondering if you could comment on some of the observations that are really important for your forecast modeling, and if there are any items that you would include on a wish list if they could be measured while there are other activities going on in that region that year that the ARCSIX campaign happens.
Yeah, I mean, one thing that comes to mind is the inability of the CAPS model to forecast ice flow distribution in a meaningful way. That I would love to be able to, I mean, I know that people are experimenting with that and now including them in forecast systems. So that's something that maybe I should be looking at. But if we could forecast changes in ice, because we want to observe the same ice flow over the whole melt season. And so I think that's critically important and something the model really can't do.
Thank you.
All right, thank you, Amy. So there is a question in the chat for Walt from Lauren Decker. How are the data sets, thickness, freeboard snow, calibrated with in situ assets? And which ones have provided the best results?
Good question. I'm not sure how much I can answer that specifically. That there has been a lot of validation and calibration work that has been ongoing, both for Cryosat-2 and ISAT-2. There were many aircraft flights, for example, as well as field observations that were taken to nail down the errors as best they could. It's a challenge because there's so much variation in the ice cover and kind of capturing how the instruments perform in different situations. There is like I talked about, SMOS is used to complement Cryosat-2 with the one product. Because thin ice is more of a challenge because there's kind of a limit to precision of what your altimeter can get. And so if you have thinner ice, your relative error is higher. And so that may not be a very complete answer, but I think that's the best I can do now. I don't know if Nathan is on. I mean, you've been a lot more involved with, at least for ISAT-2 and maybe for Cryosat-2 as well. So if you have anything to add there, I appreciate it.
Sure. Yeah, I guess I would add that I think you touched on this earlier, Walt, that the error sources are different and they vary temporally and spatially. We did just go through this exercise for ISAT-2. We had our end of prime mission and mission extension, where we looked at seeing whether ISAT-2 met its mission success criteria, and one of those was a sea ice freeboard accuracy requirement. And we did make maps of how the uncertainty in the freeboard varies. It's mostly spatially, has to do with the number of leads within a given area and then the surface roughness. And so we have made pretty good progress in quantifying this for ISAT-2. and we're looking to write this up as well. Cryosat 2, I think, is a lot more tricky. It's a lot more difficult because it's not just the surface roughness. You also have factors such as layering in the snowpack, salinity. And so again, I think it's going to vary spatially and temporally and be good to quantify that uncertainty, but difficult. And I think in a way maybe more difficult than ISAT 2.
Excellent. Thank you all for this really great discussion. Next, I'll pass it over to Cynthia for community updates.
Sure. Yeah. So we're down on our last 3 minutes. So would like to open the floor for any announcements or updates from the community. We invite all meeting attendees to share announcements, recent findings, or ideas for collaboration, requests for future meetings, or anything that you wish to share or ask. Okay, I actually have an announcement for the group. So the Arctic Research Program at NOAA, GOMO, Global Ocean Monitoring Observing, we're hiring right now. So I will share the link in the chat. So yeah, please spread the word that we're looking for a director at the Arctic Research Program at NOAA. And Betsy has an announcement in the chat. Please consider joining the SIPN mailing list as well. The link is in the chat. All right, well, thank you everyone. And I hope you enjoyed that meeting as much as we did. And we hope to see you again on our next Sea Ice collaboration team meeting. Thanks everyone.
Thank you.